Okay, the main purpose of this lab was to determine whether or not students could accelerate at a constant rate. Now, in the Vernier Logger Pro resources topic, I showed how to do the video analysis, the mechanics of it, with Braxton running across the screen at a constant velocity. Now, how do we answer this question about whether or not they can accelerate at a constant rate? Well, we're going to look at a couple videos. I picked this one, Michael Bolton. Okay, he slowed down and almost came to a stop. I had to skip a frame when plotting these points. Again, the scale is 2 meters here. So this is what we get. Actually, this is not what we get. We get just this graph to start off with. But I go insert graph. I change this to x, because x direction, or sorry, x velocity, right? And I get that graph. Then I go page, auto arrange. Now I have this graph. I'm also going to auto scale this one from 0. So now, how do we answer the question, does this have a constant acceleration? Well, if it's a constant acceleration, the velocity versus time graph should be linear. Well, this looks pretty linear, especially in the middle portion here, right? And you might say, Harmon, you're crazy. This is bouncing up and down. Yes, I know. Logger Pro velocity versus time graphs from video analysis or from a sensor, they always have this variation in them, right? They always have this variation. Overall, the general trend here, though, is fairly linear. Now, when you put a fit line, it changes your auto scale, right? So fairly linear here. About 8.5, negative 8.5 meters per second was his acceleration. Initial velocity about 3.8 meters per second, according to this. Now, you might say that's not a very good correlation, and it's not technically on paper, but it's because of the variance in the point. The variance is kind of a measure of how far each point is from the trend line. So there's a lot of variance in the velocity calculation. There's not a lot of variance in the position calculation, right? So what can we do with this to determine the acceleration? Well, we can do something called a curve fit, which I know Mr. Coleman's kids use a lot. Typically what we did in my class was we made a new calculated column, right? This is a side opening parabola. So, technically we're supposed to square position, but anyhow, let's not do that. Let's do a curve fit. So we'll do a curve fit. And this allows us to try different mathematical functions, allow us to try them on top of our curve to see how they explain it. So this looks to me like maybe a quadratic. It's not linear for sure. It could be quadratic. Let's do tri-fit. Okay. It puts the line on there, and it tells you the correlation. That's a great correlation. I'm going to hit OK. So now I have a curve fit up here. All right, we've got a curve fit and a line fit here. Now, these equations matter. X equals AT squared plus BT plus C. Okay, I'm going to take a screenshot of this right now. Alt print screen, and I'm going to put it into a file and so I can look at it later when I'm at home. All right, actually, I'm also going to print this out right now while I'm in the lab. 07 color, and that way I'm going to sit down and make a second half video of this, and we're going to talk about what A, B, and C mean, what the slope and y-intercept here mean, and how they compare to one another. So at the end of the day, this is a pretty darn constant acceleration. I don't think you could get it much more constant. And you're going to do this for 2 videos, right? One slowing down, one speeding up. And if you made a special video for fun, you can analyze that as well. I'll make a video a little bit later tonight, hopefully, showing you how to write this up, how to analyze this data. and we'll be in good shape. All right? All right. Talk to you guys later.